Hello everyone, today I'll be presenting our project on page replacement algorithms. Today we will explore page replacement algorithms, the techniques operating system use to decide which mirror pages to keep in RAM and which to evict. This presentation walks us through the classical algorithms, the real-world challenges, the modern optimizations, and future trends. Performance impact of page faults. Even though most memory accesses take only around 200 nanoseconds, a page fault can take over 8 milliseconds, which is 40,000 times slower. Even a tiny fault rate like 0.1% dramatically increases the effective access time. This is why choosing the right page placement strategy is critical. Rare faults dominate overall performances. Fast in, fast out, the FIFO page replacement. FIFO is the simplest algorithm. It evicts old page first using a key. It's fair and fast to implement, but it ignores the locality. It doesn't care how recently a page was used. As a result, FIFO often causes high fault rates and is rarely used in practice for performance-critical systems. Bilardi's anomaly, the FIFO page replacement. FIFO also suffers from Bilardi's anomaly. Sometimes adding more memory actually makes things worse. For example, in the drawing that's shown in our slide, the example shown, 3 frames cause 9 faults, but 4 frames cause 10 faults. This counterintuitive behavior happens because FIFO doesn't preserve useful pages when memory grows. The optimal page replacement algorithm. The OPT is the theoretical best algorithm. It always evicts the page that will not be used for the longest time in the future. It gives the lowest possible fault count and is immune to Bilardi's anomaly. But it is impossible to implement directly because the operating system can see the future, so OPT is mainly used as a benchmark. The theoretical limits and practical approximations. This slide explains the gap between theory and practice. We cannot know future access patterns, so OPT stays theoretical. Instead, we approximate OPT algorithms like LRE, which rely on past behavior to predict future access. The least recently used, which is also known as LRE, LRE assumes that least recently used page is the one least likely to be needed soon. It works very well on programs short temporal locality, meaning recently used data is likely to be reused. LRE performs close to OPT but requires hardware or software support to track. It requires hardware and software support to track recurrency. Now for the pure LRE implementation mechanisms, there's two. As you can see on our slide here, there's the counter-based approach and the doubly linked stack approach. These two main implementation mechanisms, the first one, which is the counter-based approach, where each access updates timestamps, and the second one, which is the stack-based approach, where attached pages move to the top of the stack. As you can see in our drawing here, or our diagram, both of them achieve accuracy but come with overhead, which is why approximation like clock are popular. Now for the clock, the circular list and the second chance. Clock is a practical approximation of LRU. Pages are arranged in circular list with reference bits. As you can see, there is 0, 0, 1, and then 0, 1, 0. The clock hand, which is there, sweeps through and clears its pages with 0. The one with the 0 is evicted. It clears it. It's the clock gives near LRU behavior with a very low overhead, making it a default choice in many OS kernels. This concludes my part, so Maya will take it from here on.
Hello, my name is Sumaya Marsalat, and I'll be taking from here. Now for comparing algorithm trade-offs and application. From this slide onward, we shift from individual algorithm to how they compare in real usage. Each page replacement method has strength and weakness depending on the workload. FIFO is a simple but often is inefficient. OBT is ideal in the theory but cannot be implemented in real time. LIU provides strong performance but requires costly tracking. Clock is a vertical version of LIU with much lower overhead. MIU works well in only specific loading workloads. This shows that the best algorithm depends on the system actually behaves. Now, for the algorithm performance and access buttons. Algorithm performance change completely depending on the access button. LIU and clock perform extremely well for the workloads with strong locality such as loops. FIFO struggles with unpredictable or scattered access. MIU helps only when the system constantly cycles through a small set of pages. The main lesson in this, the access pattern influences performance more than the memory size alone. Now, for the stack property guaranteed improvement, LIU and OBT both follow the stack property, meaning that when memory increases from n frames to n plus 1 frames, the new memory set always includes the old one. This guarantees constant improvement, and also adding memory never makes the performance worse. This also explains why these algorithms do not suffer from Brady's anomaly. Now moving to the other slide, finding the sweet spot. This slide compares FIFO, clock, and LIU based on the decision time and fault rate. FIFO is quick but inaccurate. LIU is accurate but slow and resource heavy. Clock is nearly mirrors LIU performance while staying lightweight. Clock ends up in the practical sweet spot because it balances speed with accuracy. Now, in the database management strategies beyond classical algorithm. In database, per LIU fails during the large sequential scans because it pushes critical index pages out of the memory. Commercial database management solves this with a split buffer boost and hints from the application. Hot data stays protected while bulk data goes into separate pool. This reduces fault rates by 15 to 35%, providing proving the domain-specific tuning can outperform standard memory. And that concludes my part. Maida will take it from here.
Hi, my name is Maida. I will continue. Smartphone page replacement. Smartphone uses a hybrid strategy. Kernel pages are pinned. Foreground apps use LRU for fast switching. Background apps use FIFO to save battery. Affected apps store their state flash. This combination results in faster app resume times better and better performance and high user satisfaction. Emergent trading, AI, and multi-time memory. The future of page replacement includes predictive modeling and new memory technologies. AI model can analyze past access trades to predict the next page, moving closer to OBT without hardware overhead. Multi-time memory such as DRM plus non-volatile memory reduces faults, penalizes, and creates new design opportunities. Comparative page management. Modern systems are shifting from blind eviction to informed decision. Application provides hints like which data temporary and critical. The OS combines these hints with hardware and signal to make smarter and efficient use. The reduced page faults and lower CPU overhead. Practical strategy and summary. To summarize, start with a strong baseline with clock, measure real performance under actual workloads. Use stack algorithm when hardware allows. Adapt policy to different access pattern. Incorporate domain knowledge for additional gains. And finally, remember the best page fault is the one you avoid entirely. The strategic approach gives both robustness and optimization. So thank you for listening to this presentation.